Hi, and welcome to Science Matters with Lawrence Krauss. I'm not recording this in the studio due to the pandemic, but at home. But nevertheless, I want to cover a variety of topics, as usual, going from the edge of the universe back to down here in the laboratory. Some of the topics I want to talk about today are ones that I have that follow up on subjects that I've talked about before, as you'll see. And the first one I want to talk about is the question of where did the water on Earth come from? As I've talked to you before about looking at water and, say, comets and other sources in our solar system, it appears that the deuterium abundance in the water there is different than the deuterium abundance on Earth. Now, this is surprising because enough comets have impacted the Earth over its history, enough icy balls, large snowballs, if you wish, to literally account for all the water on Earth. So there's no problem getting water to Earth, but it appears that the water on Earth is not necessarily from those sources. Now, the other problem is, of course, that any water one might have thought that existed on or near the Earth early in its history would have long ago been evaporated because the temperatures as the sun was forming was incredibly hot in this region, and water is volatile, obviously. And so there's a notion that there's a zone in our solar system called the snow zone, basically, which determines the snow line, I should say, which determines the difference between where water is ice and where it's liquid. And the presumption is that most of the water on Earth was delivered from outside the Earth through that snow line from icy hydrous comets and other systems. And as I say, there is that problem with deuterium. Now, it turns out that there's several different cometary sources, and some of them have deuterium which is comparable to the deuterium abundance in hydrogen in heavy water, if you wish, on Earth, and others are not. But recently, a group at Hokkaido University have suggested something quite different, which is quite interesting, both for the understanding of water and maybe even understanding of fossil fuels inside the Earth, which have always been felt to come from, obviously, living things. But if you look at this first image I'm showing, it's a nebula, a region outside an early forming star, and lots of, as I've talked about also, not only is water abundant, but also organic materials, the base of amino acids and other things have been discovered. So there's tons of organic materials as well. And what the Hokkaido people did was to take a mixture of materials like the organic materials, the precursors to life on Earth. They're just water, carbon monoxide, ammonia, and things like that. Take such a system, expose it to UV rays, and compress it, and then heat it up, trying to mimic the conditions during the early formation of our solar system. And what they found was that in that system, as it was compressed and then heated up, and I want to just show you sort of a little sample they did in the laboratory here, heating it up from 100 degrees Celsius to 350 to 200 to 350 to 400. What they found was that as they heated that previously highly compressed system, which had been subject to UV rays, as they heated that system up, it segmented, and basically water and oil separated out. And they have argued that, in fact, from inside the snow line, organic materials heated up in the early solar system that were delivered to Earth, the same organic materials that may, in a different form, have formed the precursor to the organic materials that make up life, those organic materials, under the right conditions, can store water. And when heated up, segmented into water and, in fact, oil. And so they have made the interesting argument that perhaps the water that we now experience on Earth did not come from outside the snow line, but rather from organic materials delivered by objects like asteroids and meteors and other things colliding with the Earth in the early formation of the Earth. And they've suggested that might also imply that there's a significant amount of petroleum, what is essentially fossil fuels, not coming from life on Earth, but rather from the primordial ooze that was created out of stars and ultimately in our early solar system. This would be really quite interesting if it's true. There's no clear evidence it is yet, but it's an example from the experiments that they've done that it's possible. And I always find it exciting when right under our noses, literally, some new possibility appears, and to suggest not only that the water that's on Earth has a different source than we thought, but also that, as I say, there may be significant abundance of fossil fuels or petroleum in the Earth that isn't from dead dinosaurs and other things. Not that we want to use it, as I've talked about, for climate change, but it's there in any case, potentially. So we'll wait and see on that story. But it could be another wrinkle on this big question of ultimately resolving where did the water on Earth come from. And that's another reason why we'll want to look at water on Mars and other places just to compare it to that in the Earth as we try and unravel the early history of our solar system and the source of the materials here on Earth that are necessary for life. Okay, that's the first topic I wanted to talk about. The second has to do with something I've talked about a lot before. And I want to look at this image here now. And this image is eerily reminiscent of those I used to see. I'm colorblind, but there are all these colorblind tests where you can look at a piece of paper and embedded in it are letters or images that I could never see. And this reminds me a lot of it, but this is not that. This is data that was taken from this object here. It's called the Atacama Cosmology Telescope. It's in the mountains of Chile, one of the driest, highest plains on Earth. And this telescope is a microwave receiver. And it's high up because you're above the water, most of the water, which absorbs a lot of the microwaves. It's a stable environment. And the Atacama Cosmology Telescope for over 5 years took data looking at microwaves from space, and they were looking at something that's been looked at by satellites, the cosmic microwave background. Now, I want to remind you of where the cosmic microwave background comes from. It's radiation left over from the Big Bang. This is a image taken by the WMAP satellite, which was a satellite designed to go up and look at this cosmic microwave background radiation. Now, the plane of our galaxy is the middle line there. And what you're seeing when you look up is basically sort of the northern hemisphere and down the southern hemisphere of the sky. It's a projection of basically a three-dimensional sphere on the sky, just like if you look at the next image, as I've shown it before, as a projection of the Earth. In this case, it's not northern hemisphere centric. It's as a picture of the Earth as you might expect from, say, Australia. But nevertheless, this is a projection of the two-dimensional sphere, surface of the Earth, onto a plane. And that's exactly what the previous image was. If we go back to it, it's a projection looking out in the sky at microwaves. And of course, the line of our galaxy is there's a lot of emission in microwaves in our galaxy. But if you try and get away from a galaxy, what this is an image from was from one of the numerous satellites that went up to try and look at microwave radiation that was left over after the Big Bang. When the universe was 300,000 years old, matter became neutral. Basically, protons captured electrons. And the hot bath of tied together charged particles and radiation decoupled. That once the matter was neutral, it decoupled from the radiation. And that hot radiation was free to travel through space unimpeded. And as the universe cooled down, that radiation cooled down. And eventually, the microwave background was discovered in 1965. This background of radiation that's now about 3 degrees above absolute zero, but was once much hotter. And that radiation, for the most part, hasn't interacted since it's come here, which is why it's probably the most important observable in cosmology. And the peak of that was the most recent satellite that was sent up, called the Planck satellite, which about 4 or 5 years ago established the best map all over the sky of the cosmic microwave background. And if you look at this image here, this is an image of the cosmic microwave background radiation. It's of course a false color image because this is microwaves. And what this represents in this image, as I've talked about earlier, at least once before, is the fact that the color represents temperatures. In the early universe, that microwave background is incredibly uniform in spite of all the different colors there, because these different colors represent differences in temperature by 1 part in 100,000. So the hot spots are 3 degrees plus 1 part in 100,000, and the cold spots are 3 degrees minus, it's actually 2.73 degrees, but that doesn't really matter. But these early inhomogeneities in the microwave background are incredibly important because they are the seeds for all structure in the universe. And this observation of the microwave background at this level of detail has allowed us to explore cosmology like nothing else. Because it's embedded in here is not only the seeds that eventually would form galaxies, and we can try and use our equations to go from that image to what we see today to try and determine what the universe is made of and how it's distributed. But looking directly at that image, we can also measure various cosmological observables to high accuracy. If you look at the next image, that represents schematically is the microwave background surface. The point, as we look out, we're looking back in time, and as we look at time before a certain time, matter wasn't neutral, and there was a plasma of matter and radiation coupled together. But then at a certain point, shown by the edge of the sphere, matter became neutral, and the microwave background was free to travel through space, and those are intervening galaxies, and there's a microwave receiver here on Earth. But the interesting thing is, if you look at that surface, if you can imagine that there are physical processes that you can understand that give objects a certain dimension, a certain size, and then you look at that surface and see how big that size is, you can learn something about the universe. And in fact, if you go back to the image from the Planck satellite, what you can see is a lot of hot spots and cold spots, a lot of little dots, and it turns out most of those dots are about 1 degree across on the sky. And that's to be expected because at the time when the universe was 300,000 years old, okay, the largest lumps that can collapse if they have a low overdensity, collapse due to gravity, are objects that are about 300,000 light years across because they're the largest objects that know that they can collapse. So you'd expect objects, the characteristic dominant size of sort of lumps that have begun to collapse at the time the microwave background reveals a picture of the early universe of 300,000 years would be 300,000 light years across. Now, we know how much the universe has expanded since the time the microwave background was created by a factor of about 1,000. And the key question is, what distance does that correspond to? And clearly, if you look at a 300,000 light year across ruler and it's much further away, it's going to seem much smaller than if it's closer. And so we can, in some sense, infer how far away the distance is from the radiation that we're receiving from the microwave background. But also it's also related to the geometry of the universe. If you look at the geometry of the universe, if you look at these universes here, these are two-dimensional images because I can't draw three-dimensional curved surfaces. But if I consider triangles drawn on different curved universes, there are three types of universes. A flat universe, in 2 dimensions, a flat piece of paper. In 3 dimensions, just a universe in which the x, y, and z axes point in the same direction everywhere. There's a closed universe, which in 2 dimensions is a sphere, and in 3 dimensions is a closed 3-dimensional sphere. Or an open universe that in 2 dimensions looks like a saddle, and in 3 dimensions is harder to picture. We, for a long time, tried to figure out which universe we lived in, and we now know by measuring the cosmic microwave background and other things that we live in what is essentially a flat universe. But one of the ways we know that is by drawing a triangle. Okay, if we draw a triangle and one end has a ruler of a known length, we can ask how large an angle will that subtend. As I told you, if it's further away, it'll subtend a smaller angle. But as you can see from these images, light rays bend inward if you go back in time if the universe is closed, and outward if it's opened, and are straight if it's flat. And by measuring that, by measuring that the largest lumps that were 300,000 light years across are basically 1 degree on the sky, that tells us basically that we're in a flat universe. That was one of the measurements of a flat universe. But there are many, many other characteristics that you can tell. By the way, here was an early cosmic microwave background image, not from a satellite, but from a balloon experiment, where you could see hot spots and cold spots, and the experimenters simulated universes, curved, open, and closed, and to see how big the apparent 300,000 light year across hot spots and cold spots would be. And you can see from the closed universe they're bigger. The open universe are smaller, but just like Goldilocks for the flat universe, they're right on. But we can do much more. And by looking at the distribution of lumps and hot spots and cold spots and how big they are in terms of magnitude physically and in terms of temperature change, one can produce an exquisite map of the microwave background. And one way to present that data is here. It looks fairly complicated. But what it is, it basically counts the number of lumps that you measure as a function of their angular size across the sky. So you see most of the lumps are at 1 degree. This is the data taken from the Planck satellite. And you can see the exquisite accuracy of measuring these things. Now, the dots are the measurements. The lines are actually the predictions that come from our best model of the early universe, fluctuations that were created by quantum mechanics due to inflation. And you can compare the predictions with observations and you can see they're bang on. But by trying to measure where the biggest lumps are, how big the next largest sets of lumps are compared to the biggest sets, and the amplitude of the lumps, you can try and measure many of the parameters of cosmology. For example, the amplitude, the amount of the temperature fluctuation corresponding to the dominant lumps of the universe, tells us the density of matter in the universe. Because early on, matter, protons and electrons, were coupled to radiation. As the matter began to collapse, it left a signature on those lumps of the radiation at the point where the matter became neutral. The radiation was hotter if the matter, it turns out the radiation emanating from those surfaces, if the matter had collapsed, is a different temperature than it would in regions where the matter hadn't collapsed. And if there's more matter, it's more strongly coupled to the radiation, and you'd see a bigger peak. So the size of the peak tells us, among other things, the density of protons and neutrons in the universe. From this, you can measure many, many, many cosmological parameters. And this has been done with satellites. And now, after 5 years of analysis, this large Atacama collaboration produced an image like this that can see about half the sky from Chile. And after a lot of analysis, which is a lot harder on the ground because from the ground there's also all sorts of foreground sources of microwaves, and you have to look through the galaxy and through the atmosphere, and you have to be much more careful to be able to separate those things out, and you need a large collaboration and a lot of time to do it. And here in the next slide you can see the collaboration that produced this paper recently, and you can see in the next slide all the kind of parameters that they try and model. They take the best cosmological model that we have for matter, dark matter, and dark energy, and try and fit those to the data they've seen. And above the horizontal line are sort of cosmological parameters that relate to the density of dark matter, or the density of dark matter that's been measured, the density of baryonic matter, normal matter that's been measured. And below the lower one of those two lines are all what are called nuisance parameters. Basically, they're noise coming from dust and other things that you have to try and extract out to find the primordial signal. Now, the reason that this new observation is interesting is it's looking at the same stuff that the Planck satellite looked at. But what's interesting is if you look at the one number in that image, H0, which is the Hubble constant, the expansion rate of the universe, in these units it's 67.6 plus or minus 1.5 kilometers per second per megaparsec, some number. But what's interesting is that's more or less precisely the number that by a completely independent set of measurements the Planck satellite arrived at. Great. But is that worth talking about right now? It is, because it's interesting, because as I talked about in an earlier episode, the Planck satellite measures a Hubble constant of something like 67 or 68, whereas measurements from the ground looking at the expansion rate of the universe by measuring supernovae and other objects in galaxies moving away from us find a Hubble constant that's larger, 70 to 72. Now, is that significant? Well, the quoted error bars here are 1.5, so you might say it's not significant. And you might say there's systematic errors that might suggest that the Planck satellite is getting a different number from the ground-based measurements. And that's why this measurement is important, because this measurement of the cosmic microwave background, totally independent of the Planck satellite, gives exactly the same number. And that suggests that at least there are no experimental systematic uncertainties that systematically move the Planck number away from what you might get from a otherwise correct reading of the cosmic microwave background. This is the number that apparently comes from the cosmic microwave background. And by the way, the other thing that the Atacama observers have done, which is interesting, they've been able to use this and our cosmological models to quote an age of the universe of 13.77 billion years old. 13.77 billion years old, plus or minus 40 million years. But the thing to understand when you look at this plot is that there's a lot of interrelationships. In order to derive these numbers, you have to make certain assumptions about cosmological models, which you're then testing with the same picture. So I'm not sure I really believe the 40 million year uncertainty of the age of the universe, but it's certainly consistent again with the 13.8 billion years that was derived by the Planck satellite. But this does suggest that discrepancy between measuring the Hubble constant by looking at the expansion of nearby galaxies and measuring the Hubble constant as deriving it from all the cosmological parameters by measuring the cosmic microwave background at large distances, that discrepancy is real in the sense that the microwave background predicts a different number than many of the ground-based measurements. Now, the key question will be, will the ground-based measurements of supernovae and other things converge with that number or remain different? If they remain different, that really will be a problem for cosmology. But as I've said earlier, I'm betting on the systematic uncertainties. But what this new observation suggests is, at least in the cosmic microwave background, the systematic uncertainties don't appear to be a problem. Two very different sets of experiments measuring the microwave background appear to hone in on the same number. Now, they use the same cosmological models to fit the data. Maybe the problem's in that. We'll see. Anyway, I thought I'd let you know that follow up on what we've done before. It was a relatively complicated discussion of something we've done before, but probably worth reviewing. Now I want to come back to Earth, and I want to talk about something that also in its own way is complicated. It's something I've kind of avoided talking about a little bit because it's a study of materials. And materials, the physics of materials, while fascinating, is somewhat complicated. I want to talk about a new observation, and here this was the picture that came from this new observation of something strange in a material that was created that's actually quite an interesting material. It's called a phase change material, and meaning its atomic structure shifts as you heat it up, and it's reversible. So at one temperature behaves like a crystal, and another temperature behaves like a glass. And since it's reversible, it could be used in electronic devices where information has to be stored and rewritten several times, because you can change the structure of this material. But what's interesting about this particular material, and I don't even know the name of it, but it has germanium, antimony, and tellurium in it, and it's got some chemical name, but it demonstrates some very weird properties of electrons in materials. Because of the collective interactions of electrons and materials, they can behave in many different ways. And that's manifested in the fact that in certain materials they're insulators, other materials are conductors, and it's the electrons that are doing the conducting, or in some materials they're superconducting. They form what are called Cooper pairs, and they behave in very strange and interesting ways. And the physics of materials, called condensed matter physics, over the last decades has specialized in trying to understand the weird properties of materials and electrons in those materials to both create new materials for better computers, better electronic properties, but also to understand the fundamental makeup of matter, and literally quantum engineer, trying to create materials that have the properties that you want, and very strange properties sometimes. Now, to look at the strange property that was just discovered, I want to take you back to a little bit of high school physics, if you don't mind. And if you do mind, well, turn this off. If I take an electron, classically, a Newtonian electron, it can have an energy 1/2 mv squared. Okay, kinetic energy. Its kinetic energy is 0 if it's not moving. If it's moving, it has a kinetic energy 1/2 mv squared. Now, the quantity mv, classically in Newtonian sense, is called momentum, as you may remember from high school. So you can rewrite 1/2 mv squared as p squared over 2m. And what that says is that the energy is quadratic in the momentum for a particle. And I haven't, but I've taken a picture of drawing that quadratic. This is how the classical Newtonian energy of an electron is as it's moving. If it's at rest, its classical energy is zero. In this case, K is the same as P. It's just a different way of writing momentum. And some people sometimes use K, sometimes use P. And the condensed matter physicists tend to use K. So in any case, an electron classically, in Newtonian sense, at rest has zero classical Newtonian energy, and as it moves up, as it begins to move, its energy increases quadratically. Now, of course, we understand as you start to move faster and faster, Newtonian mechanics breaks down and you've got to use relativity. And relativistically, the equation is different if you go to the next as we go to the next slide. In fact, that Einstein derived this famous fact that E equals mc squared. Well, if a particle's at rest, E equals the rest mass times c squared. And if you look at this, this is actually the relativistic form of energy. It's the energy squared is equal to the momentum squared times c squared plus the rest mass squared times c to the fourth. And if P is zero, if the object at rest, then E is equal to mc squared. If you had an object that has zero rest mass, like light, then E is Pc. But because the actual equation for energy is quadratic, E squared equals Pc squared plus m squared c to the fourth. If I set m equal to 0, I get E squared equals P squared c squared, and that has two solutions. E equals plus c Pc and E equals minus Pc. Now clearly the relevant physical solution is plus Pc, because we say objects that are moving have positive energy. And so for a photon, E equals its momentum times c. And photons have energy, and that's a relationship for them. Now, what happened in 1929 was a physicist by the name of Dirac, one of the greatest physicists of the 20th century, tried to understand electrons in a relativistic sense, tried to understand the quantum mechanics of electrons in a relativistic sense, and he came up with an equation we now call the Dirac equation. And the Dirac equation was really strange because it suggested there were two sets of solutions. There were solutions of the Dirac equation with positive energy and solutions with negative energy. Now, we know electrons, we have electrons. There were actually four different solutions, the Dirac equation for an electron. Electron with spin in one direction, electron with spin in another direction, and then some weird state with negative energy that had spin in one direction and spin in another direction. Now, Dirac tried to understand this, and he said, well, maybe empty space, he thought, we now call it a Dirac sea, maybe empty space is kind of full of all these negative energy particles that come up to zero energy. We don't see them, okay? When you pump enough energy into an empty space, you can kick an electron up from that sea into being a real electron. And as I've shown here, say in that positive band, what does it leave? It leaves a hole. It leaves a space where there used to be an electron in that sea. What is the hole? Well, the hole is the absence of an electron. Since an electron has a negative charge, that would have positive charge. And this is how Dirac ultimately predicted, although he didn't believe it, that there should be particles, we now call them antiparticles. For an electron, there must be an antiparticle called a positron. And a year or so after he made that prediction, positrons were discovered. But the Dirac sea was just his, if you wish, his kind of mathematical way of trying to picture how to understand how when you dump energy into empty space, you can create an electron-positron pair. It was just a kind of weird picture for that formalism. But in materials, that formalism is particularly useful because electrons, you have lots of electrons that are in some ground state of the system. They're interacting in some collective state, and you can create weird kinds of properties as you excite particles out of that ground state, just like in the case of an empty space. If you put energy in empty space, you might kick out an electron-positron pair. In this case, in a material, you might kick out an electron, but an electron interacting with all sorts of other electrons, leaving a hole-like object that's also interacting with a lot of other hole-like objects. And those dressed up electrons and those dressed up holes in materials can act very strangely and produce fascinating properties of materials. Now, in fact, what's been seen in materials is that under very special circumstances, electron states have been found that appear to be massless and obey what's called the massless Dirac equation. Their energy, if you wish, goes like PC. These collective excitations act like they don't have mass. Now, what makes that interesting, if you go to the next slide, is that in certain materials that produces interesting properties. It turns out that the zero mass, zero rest energy, zero mass states are a property of are due to the symmetries of the material. They're very special states, and those weird zero mass kind of excitations allow very interesting conductivity. Graphene is a material, a two-dimensional material made of carbon, and because of its two-dimensionality, you can show by the symmetry of graphene that there should be these essentially zero mass excitations, and they allow graphene to have a very special high conductivity, which is one of the reasons graphene is so interesting, and the people who first were able to synthesize graphene, if you wish, won a Nobel Prize, the physicists who did that. More recently, other materials, here's the cover of Physics Today. What is this? It's once again showing that energy plot with that triangle-like structure, and this is what's called a three-dimensional topological insulator. It's a material where, because of the properties of the electrons and the materials, there's a very special, if you wish, zero mass kind of excited state caused by the symmetry of the system, and it means that inside the material it's an insulator, but on the surface of the material it's a conductor. Now we come back to the new discovery of this material, which I say is an interesting material because it's reversible. Under heat it goes from kind of a glass-like structure to a crystalline structure. And what was discovered, as you can see from the right-hand side again, in the crystalline state, there's what's called a topological, because it's by the symmetry of the system. It's related to the topology and the symmetry of the system. There's a zero mass-like excitation, causing to be highly conductive, whereas the amorphous state is not conductive. And so here you have this case of a massless excitation in a material that could be very useful for electronic materials, because it's reversible. You go back and forth, and in one case it's highly conducting, in another case it's not, and it's related to the discovery of these topological states, these massless excitations of electrons. The electrons are not really massless, but when you dress them up, they behave in the material as if they're massive, because particles inside materials behave differently than they do outside materials. Just like I told you once a long time ago that the Higgs particle is very interesting because it means we're in a bath of fields, and elementary particles behave differently in that bath of fields, acting like they have a mass when the Higgs field is there in empty space, and if it wasn't there, all the elementary particles would be massless. Similarly, in materials, electrons can behave differently. As I've talked to you about in a superconductor, photons act like they have a mass. When a photon goes tries to traverse the material in a superconductor, due to the interactions with electrons in the material, the photon acts like it has a mass. In this case, the electron self-interactions in strange materials causes excitations that are massless, that act like they're massless. I told you it's complicated. Condensed matter physics is complicated, but what's really exciting is that by looking at these materials and using quantum mechanics, we can try and create interesting materials where electrons have very strange behavior, which is going to affect the technology of the 21st century. Well, those last two topics may have seemed very complicated, so I want to return to something that's a little more down to earth. It's not quite down to earth. If you look at this image, these are images from Mars and the Moon. The upper left-hand image and the lower left-hand image are from Mars, and the right-hand image is from the Moon. These, we think, are lava tubes. What are lava tubes? Well, before we go into lava tubes, I think I have one more image. This is a lava tube on Mars, and actually you can see, if you look very carefully, you can see where it's been broken through, and light now shines deep down. And lava tubes are fascinating. They're fascinating to me because I've actually visited some. I live near Mount St. Helens. I live in Oregon, and I live near Mount St. Helens. This is an image of Mount St. Helens. And if you go near Mount St. Helens to a place that was discovered, I think, when a farmer's tractor fell through, there's a thing called ape caves. And if you walk through, I've gone through it, it's a 2-mile tunnel. The lava, after a volcano goes up, the lava flows. On the outside, the lava cools off, forming a hard crust, and the lava, the molten lava flows through it, and eventually might all drain out, and it leaves this incredible lava tube. It's an amazing thing to walk through. The one I've walked through is about 2 miles long in the total darkness. The ceiling is sometimes 20 meters, 10 to 20 meters high. Huge things where the lava once came through, not with the most recent explosion of Mount St. Helens, but thousands of years ago with an earlier explosion of Mount St. Helens. And if we go back here, what's been discovered is that there are similar lava tubes that look like they're there on Mars. And even because Mars and the Moon both had volcanic activity a long time ago, neither of them has volcanic activity now. But a variety of researchers, again at a Japanese university, have suggested these lava tubes, by the way, are much bigger because of the difference in gravity in Mars and the Moon. Whereas the circumference of the lava tubes that I walk through is maybe 10 or 20 meters, in Mars and the Moon in particular, they can be 10 to 100 times bigger. They can be formed in two different ways, from early volcanoes, or as this one, if you go back to the image of the Moon that looks like that collapsed hole, it can happen due to a meteorite impact, which effectively liquefies the material. And both from early volcanoes and those regions, you can have huge enclosed tunnels or caverns. And what these researchers have suggested is that these could be extremely useful if humans are ever going to explore and live in these systems. Because unlike Matt Damon on Mars, one of the big problems if you actually have a long-term base on Mars or the Moon is that the Mars and the Moon don't have atmosphere or magnetic fields that shield us from otherwise harmful radiation. And one of the big problems of having a long-term base on Mars, for example, is not to die of radiation sickness. One possibility is to build large bases inside those lava tubes, they've suggested. That's a useful idea. First of all, they're stable. They're huge. You could have a whole city in them. They're that large. So you could build literally a whole community, protected, because it's underground, if you wish, from the radiation, but also because it's a relatively controlled environment, it won't change its temperature as much during the day and night, which in the day-night changes in temperature are extreme for both the Moon and Mars. So this is an exciting option, perhaps one day, if humans go to these systems. And if you go to the last picture I want to show you, one of the suggestions for an American system actually is to send a rover to actually drop to dig, basically go down into one of these lava tubes, in one of these collapsed, if you wish, collapsed craters, and explore it. I find it fascinating, and as I say, I found it fascinating because I've been in the lava tubes on Earth, and since I find it fascinating, I wanted to talk about it. I don't know if you'll find it fascinating too, but they're extremely interesting things, much closer to home than the extreme ends of the universe, in materials in the laboratory, and even as close as our Moon, where we one day might imagine city-like structures, colonies, protected from radiation. You know, I'm not a big fan of human space exploration for science, but there may be other reasons for adventure to want to have a colony on the Moon. And so if we do, maybe a lava tube is the way to do it. Either way, science matters. Take care.